let's now go to Brendan. Brendan Murphy is a professor in the School of Mathematics and Statistics at University College Dublin and a member of the Irish Epidemiological Modelling Advisory Group. And
is my screen share working?
Yours, yes. Yes, that screen share seems to be working fine. Thank you.
Right. I'll put on my video as well. Just okay. Thank you for inviting me to give this talk. The focus of my talk is going to be quite different to the previous one in that I'm mainly going to be talking about the modelling that we've been doing in Ireland, giving a high-level overview, but I will interject with various other aspects like the previous talk. So just to give some background, the first case of COVID-19 in Ireland was confirmed on the 29th of February. And basically, the number of cases stayed very low for a few weeks after the first case. And on March 11th, there was a meeting held in the government buildings where the chief medical officer basically set up the Irish Epidemiological Modelling Advisory Group to help advise the National Public Health Emergency Team, who then advised the Irish government about the COVID-19 crisis. And the group was chaired by the president of one of the universities in Ireland, Professor Philip Nolan from Maynooth University. When the group was set up, we had 3 working groups within the Irish Epidemiological Modelling Advisory Group. There was kind of a core modelling group. There was a group of mainly economists who looked at healthcare demand. And then there were a lot of people who had geospatial expertise who looked at geospatial data visualization and geospatial data modeling. And obviously there's quite a bit of overlap between the work of the different working groups within the Irish Epidemiological Modelling Advisory Group. The remit of the group that got set up was included a number of things. 2 of the main things were gathering evidence and monitoring the epidemiological characteristics of the outbreak, both in Ireland and internationally, and then developing epidemiological models for the outbreak in Ireland and looking at the impact of different public health interventions, etc. over time. So we were basically starting at, a very low base, and we very quickly scrambled together a group of people who had a lot of skills that were going to be useful for addressing these needs, basically, for the Irish government. Much of the modelling that's happened in the group has fallen into a number of different kind of categories. One aspect that I've been very much involved in is modelling the case data, the deaths, hospitalizations, and other kind of data that's been collected about how the epidemic was happening in Ireland. We spent a lot of time looking at various ways of estimating epidemiological parameters, not just including the effect of ore at a particular point in time, but that was one of the focuses of the group. We had to develop models for future scenarios, so what would happen under various scenarios, in particular as the effective ore value changed over time. What would the impact of that be? We also had to look at what the impact of the various scenarios would be then on the Irish healthcare system. So that was a very important aspect because we were very conscious that a fast-growing epidemic would have meant that the healthcare system would have reached capacity, in particular in intensive care units, very, very quickly. And we had to look at ways of avoiding that. And then looking at the geospatial aspects of the epidemic in the country. So even though Ireland is a relatively small country, there is quite a bit of spatial variation in how the epidemic kind of unfolded throughout the country since it started. So in terms of data, there was a lot of work put in initially in the group looking at data. And it was very important that the available data was collated in a central repository so that anyone doing modeling of the epidemic would have access to it. And, you know, there was a lot of work done at the initial phase of the epidemic to do this so that we could get as much data to the modelers in a useful format as we could. And it turned out that the Central Statistics Office, that's the Irish equivalent of the Office of National Statistics in the UK, they were a very useful kind of resource for this, that they basically acted as kind of a hub for all of the data that was being generated in different parts of the health system, in the testing system, etc. And it was, you know, a very practical way of using their expertise to help address this national need. A lot of the data that we've been looking at when we're modeling the epidemic to advise the National Public Health Emergency Team has fallen into a number of categories. We have the case data, which is kind of the daily data that comes in on the number of cases that are happening in the country. And this data has proved to be very useful and very important in modeling and advising people on what status we're at the moment. This data can be looked at in many ways, and you know, the obvious data that's reported in the media every day is looking at the cases by the date of reporting. During the epidemic, the time from when people were tested till when their results were known actually varied quite a bit. So if you look at the data in Ireland by the date of reporting, at certain stages in the epidemic, there was very long lags for some cases from when the samples were collected to when the results were reported. So you do get kind of unusual spikes due to this. And at one stage, we actually had to outsource some of the testing to Germany to clear the backlog. And the time from sample collection to reporting is fairly steady at this point. So we found actually over time that, you know, analyzing the data by lab specimen collection date gave a much better picture of how things were working, but there is a lag because of that, because you have to wait from you basically when you're backdating samples to the lab specimen collection date. A lot of the data had symptom onset dates as well, but we found that in a lot of cases those were missing or possibly inaccurate. So with the case data, we found the lab specimen collection date was actually a very important aspect of analyzing the case data. Likewise with the death data, there was obviously the deaths are reported on certain dates, but then actually the date of death data ended up being more important. But again, occasionally this has lags in it. We also had very good hospitalization data available and testing data, and then other data. Other data has kind of evolved over time. There's a lot more spatial data happening from, I'll talk about this more later, from mobile phone. We've also looked at traffic data. There are sensors on a lot of the major roads in Ireland, and you could see the impact of various interventions on traffic and travel basically throughout the various stages of our lockdown. In the early stages of the epidemic, we had very little data available. We really had the cases that were happening every day as they were reported, and then very soon after being mapped back to the lab specimen collection date. We actually started off with very, very simple models for the case data, just to give government very short-term forecasts of how the cases were going, basically, how quickly they were growing, and basically how many to expect, say, for the next 5 days going forward on each day. So we started off with actually just a very basic Poisson model where we had the mean that was time varying, and it followed various parametric forms, basically, the mean. We actually had three kind of competing models that we felt captured, could potentially capture the epidemic in the short term. We had just an exponential model, a logistic model, so that we'd have an increase around us, and then a symmetric peak, and then a decrease, and then a Gompertz curve where we had kind of a steep increase and then a slower decrease after some peak. And on a daily basis, we would have fitted these models and updated them and actually looked at various criteria for which models were the best and assessed the predictions we were getting, and possibly even combined. In some periods, we would have combined the predictions from the multiple models when there was two models that were, or three models that were competing and almost equally good, to just give short-term predictions on how many cases to expect, and consequently how many hospitalizations to expect going forward. In the early stages of the epidemic, this actually was quite useful. Like very early on in the epidemic, we were in a period of exponential growth. We had a doubling time of about 3.5 days, and it was useful to give predictions telling the government how many cases to expect going forward. And then very quickly, the Gompertz model started to kind of give very practical predictions. And it actually served very well for a long period of time. So it's a very straightforward model. We have basically Poisson counts every day. And then the Gompertz basically gives the shape of the mean over time. But then we got to the point where the Gompertz kind of kept decreasing and the cases kind of went flat and started increasing later on. So it no longer really gives good performance, but it did serve as well for quite a long time. So that was just modeling data on a national level, just to get a good overall picture of the epidemic. We also fitted this model using a Bayesian approach, not just the maximum likelihood that I talked about, because that gave us a better handle of the parameter uncertainty. The parameter estimates for a lot of the parameters, even though it was only 3 parameters in the model, they had a lot of uncertainty in them. And over time, basically, we found, one day's data could change the parameters quite a bit. So we found the Bayesian model gave a better characterization of the uncertainty in the model, and it allowed us give better calibrated prediction intervals, and we could get posterior distributions for various things like when would we expect the peak in the number of cases to happen and how large would that peak be. So here's actually just a picture of posterior densities of when we would have expected the peak to be, and it's about 38.5 days into the epidemic, and then the height of the peak, and it's suggesting the height, the mean, the Poisson mean would be about 650 or thereabouts. So the actual peak observed counts could be quite a bit higher because the mean and the variance of the Poisson being equal. That's estimates that were given in early April when we were getting close to the peak. That's just an example of the type of output we were able to produce. The Bayesian model also allowed us develop county-specific models where we were able to have a hierarchical model that each county had its own parameters, but there was a certain amount of borrowing of strength or borrowing of information across counties when we were getting estimates for counties that had very little data. So we developed a Bayesian hierarchical model for the county data. So just to give some context, I know this is an unusual map of Ireland because I'm only showing the 26 counties in the Republic of Ireland. I've left out the 6 Northern Irish counties. And I've colored the counties by population. And in some ways, when I produced this plot, I said it's a terrible choice of color scale for the plot, but it actually does reveal a very important aspect of modeling the Irish data and handling the epidemic in Ireland, is that even though the population of Ireland, the Republic of Ireland, is a little bit less than 5 million, it's about 4.9 million, a huge proportion of the population live in Dublin. So we've the Dublin is county over on the east coast, that's in bright yellow on this plot, and every other county is quite dark. So the population of the country is very much, there's a huge number of people living in the capital city. Cork, which is the largest county, is the second most populous county in the country. And you can see the commuter belt around Dublin, those counties are a little bit lighter than some of the other ones, and Galway over on the west coast is also a little bit lighter. But I think actually, even though when I produced the map, I thought this is a bad choice of color scale, I think it actually does capture the population and its distribution in Ireland quite well. So we developed a model that each county would have its own specific mean curve in the Poisson model, and that there would be information shared across them. So it's a slightly different model to previously, in that I've just taken the first parameter of the Gompertz and included the population county in it, so that the alpha parameter has a similar meaning across the different counties. We had a hierarchical model where the parameters for each county had a common prior distribution, and that kind of allowed the estimates of each county to use kind of their own information, but also borrow information from the other counties in their estimation. So, and we fitted these models using Markov chain Monte Carlo, specifically using Hamiltonian Markov chain Monte Carlo as implemented in the STAN software. And this allowed us basically get posterior samples for lots of the model parameters for each county. And I'm showing you actually just our estimated disease curves for the 4 most populous counties in Ireland as estimated in May, late May this year. And we can see, for example, that there was quite a different experience in the 4 counties I've shown. Dublin had a very, very high peak of over 20 cases per day in very early April. Limerick's peak was a lot lower. It was more like 7 or 8. And then you say Cork and Galway were much, much flatter than that. So that was one of the things we could produce from our Bayesian model. And we also had uncertainty bounds around these and prediction bounds, but I've left them off just to declutter the plot today. We were also then, now this is kind of showing posterior estimates from May, so it's kind of after the peak happened. But even before the peaks happened, we were able to give posterior summaries of when we expected the peak cases to happen in each county. Now, for the 4 most populous counties, the peak happened pretty much in early April, but in some of the more rural counties, it was much, much later. It was as late as late April. And then we also had posterior kind of estimates of how large the peak was going to be. So amongst the most populous counties, Dublin had the largest peak, as we saw in the previous graph. But some of the counties close to the border with Northern Ireland actually had larger peaks, basically, but that's per 100,000 population. And we were also able to produce maps for any specific date of where we expected the incidence to be. So this was produced in May as well. So at this stage, we had kind of a lot of the rural counties were the highest, but they were at a level of about 5 daily new cases per 100,000. So that sort of modeling was very useful to feed to the public health people in the health service in Ireland, where they could see where the highest number of daily cases was happening around the country. They were particularly interested in monitoring the 4 most populous counties, but they could also see in rural counties then that at various stages that there were kind of hotspots of cases. Another aspect of the work that was going on in the Irish Epidemiological Modelling Group was to produce synthesis documents on the values of epidemiological parameters in the COVID-19 epidemic. So this was a group of public health researchers and actually veterinary medicine researchers who who actually have a lot of experience of dealing with, disease outbreaks. They kind of combined their knowledge and information to effectively do a very large search of the literature, and they continually updated this literature search to get the most up-to-date kind of understanding of what the values of various parameters that govern the epidemic, what were the values that people were seeing internationally. So we were interested in things like the incubation period, latent period, generation time and serial interval, R0 and the effect of R at times in the future, and the proportion of infected people that were symptomatic. That was something we spent a lot of time discussing at meetings of the Irish Epidemiological Modelling Group. And then the length of the infectious period for various groups, and how infectious symptomatic and asymptomatic people were as well. So there was a lot of work done to get to find out what were the values of these various parameters that would go into any modeling that I'm going to move towards now. And just to mention, a lot of the work that they did has been uploaded to medRxiv, and some of the work has been published. I know that the paper on the incubation period of COVID-19 has appeared in BMJ Open relatively recently. And then the papers they wrote, or the synthesis documents on other epidemiological parameters, are on medRxiv. And this is just a subset of the ones they wrote. I think they wrote about 8 in total. You can only get so far when you're monitoring an epidemic modeling data. So we also had to develop a disease spread model to look at the epidemic up to date, but also going forward, so that we can get a good idea of how the disease is progressing in the country. So the applied mathematicians that were involved in the Irish Epidemiological Group developed a SEIR model to model the spread of COVID-19 in Ireland. And their model had a number of compartments and obviously a number of time periods where the compartments kind of have various roles. And this is kind of the model that we've settled on after a number of iterations, basically. And I'll talk, the model has recently been extended again, but we developed this SEIR model that included asymptomatic fraction and symptomatic fraction, and then different trajectories for the symptomatic people going forward. And the model it was basically a system of differential equations, and these are the differential equations governing the behavior of the model going forward. So this was the SEIR model that was developed to help get a good understanding of how the epidemic has progressed and will progress in the country. And interestingly then, this is where the huge amount of work that was done on studying the epidemiological parameters fed very much into the modeling at this point. So the work that was done by the epidemiologists on understanding the models, the epidemiological parameters, fed very much into the choice of parameters in the SEIR model when we were going forward. The contact rate was basically calibrated, and basically we looked at the effect of the various interventions on the time varying beta T. Basically, we allowed a time varying beta T to allow for the non-pharmaceutical interventions that we used in the country. So we were able to basically capture the effect of the various interventions in the country with this time varying beta. We looked at calibrating the model a number of ways. In the early stage of the epidemic, it was just exponential growth. So we had a constant beta value to capture the exponential growth we were observing. Later on, after a very short period, as I said, the mean of the Gompertz that we were using in our database model actually was used to work out the time varying beta, basically. So we actually set this up as an inverse problem. So this is where the applied mathematicians and the statisticians started kind of liaising very closely on this. So once we had a good smooth fit, it had to be a smooth function to the data, modeling the case data. And we generally found modeling the case data by lab specimen collection data was the best. We then basically used this, we set up an inverse problem where we were able to use the fit to the data to invert the set of differential equations to determine a time varying beta t in our model. So that's kind of, and how do we do that? So if we had an SI model, you can basically solve, if you have an incidence function, you can solve for beta t by solving this equation here. And we used a very similar idea for our SEIR model. We just had a lot more calculations to actually invert our model to get our time varying beta t in the SEIR model. And once we have a time varying beta t, we can get a time varying effective OR value as well. And we have actually a document that's up on the government webpage, basically going through how we do this. But basically, we're able to use our data model that was basically based on the Gompertz early on in the epidemic. I'll talk about extensions we've been working on since, to come up with a time varying force of infection or transmission rate, and consequently an effective OR over time by solving a number of numerical equations. So for example, here's a plot of how our case data went early in the epidemic, and then and that's the Gompertz function that was fitted using it's actually showing the posterior distribution of the Gompertz fit, so it's the Bayesian model. And then this gives us an estimate of OR basically over time, including uncertainty bounds. Now, the way we found those uncertainty bounds was we had the posterior distribution of the model parameters from the Gompertz, and we also had the range, the plausible range for all the epidemiological parameters. And we basically, by taking samples from the posterior and from the epidemiological parameters, we were able to basically look at the various values of OR we were getting and get bands for the estimated OR in a time varying manner at different points in the epidemic. So this was a nice example where we were combining the data we were getting on the epidemic with the SEIR model that had been developed by the group to get a handle on how the effective OR was at various points in time throughout the epidemic. We also then kind of projected forward in time. We were able to present various scenarios to the National Public Health Emergency Team, where we were able to show if the effective OR increased to some value, maybe for some time period, what would actually happen. And then you may need to have a new intervention to bring OR back down to drop the number of cases. So this is an example that on May 18th, which is where the data ended, if we let OR go back up to 1.6, we'd have had a peak. And if 4 weeks later, we brought in a new lockdown to bring it back down to 0.6, this is what we would expect to happen going forward. Or if we kept OR at a more manageable level of 1.2 for a 4-week period and then brought it back down to 0.6, this is what we would have expected going forward. So we were able to run lots of different scenarios of if this happened to OR, what would actually happen going forward. We also took both the predictions from the database models and the SEIR model and fed them into a model of the healthcare system that was developed by members of the Economics and Social Research Institute, who were a lot of members from that institute were involved in the epidemiological modeling as well. Now, this is just kind of an idea of the type of model we were using. They've actually developed quite a bespoke model that takes into account capacity in individual hospitals, staffing levels, staff rotas, geography of where the hospitals are located, where we were basically able to feed the predictions we were making for the number of cases into basically a model of the healthcare system and to predict where we would expect the demand to happen and how large the demand would be over time. So there was the models of the data that we were looking at were feeding into healthcare demand modeling as well, and that helped with planning healthcare during the epidemic. Since the middle of the summer, the Gompertz function that we were using to model the cases kind of no longer provided an adequate fit, and that was a key part of our SEIR modeling that we were using for modeling future scenarios. So we actually had to move to a more flexible model for the cases. So we started using generalized additive models, which basically allow us, instead of assuming a particular parametric form for the mean of the number of cases over time, we're basically assuming a smooth function for the number of cases over time. And then we also looked at, instead of just restricting ourselves to the Poisson, allowing for distributions like the negative binomial that would allow for more dispersion, over dispersion in the number of cases. So the generalized additive model basically assumes that the mean number of cases over time follows a spline, either a cubic spline or a thin plate spline, a one-dimensional thin plate spline, or one-dimensional analog of the thin plate spline. And basically, we had the Poisson and the negative binomial, and that actually was well able to match the case data in recent times. And because the function we're using is smooth enough, we're also still able to use our SEIR-based estimate of RT. So we're still able to match the differential equation model with the data. So here's a plot of the cases with, I've actually got 4 spline fits shown. I have the Poisson cubic splines, Poisson thin plate, negative binomial cubic and negative binomial thin plate. And they're all giving very similar fits. There's subtle differences in various points, especially in the recent days. This is actually only produced on the for data up to the 3rd of September. And we're able to then use these fits to get our estimates of RT, basically. And then we can also take our model at that time point and look at scenarios going forward and provide those to the National Public Health Emergency Team. We've also just developed an extension of the SEIR model that has different compartments for different age groups. So we've taken kind of we've broken the ages of people into a number of bins, and we've developed an age cohort SEIR model. And this allows us to model different experiences for the different age cohorts. We can also incorporate kind of information about close contacts using kind of studies like Polymod that has looked very closely at the interactions between different age cohorts. And we're also it allows us to look at different susceptibility and infectiousness of different age groups. And also we can look at different interventions for different age groups. Things like school closures would have a much bigger impact on the younger age groups than the older ones, and we can now include that in our modeling. The public got very hooked on RT, the effective error rate, and I think, that was something that was very interesting. And I know the previous speaker mentioned this too, that everybody talks about OR nowadays. We did look at a number of approaches for estimating OR. We looked at things like the Wallinga and Sunis method. We had our SEIR-based estimate. We looked at the Flaxman model that was published in very recently, the Imperial group that developed that, but we extended it to include Ireland. They didn't have Ireland in their original set of countries, but we actually included that. And we've been looking at their recent OR package called Epidemia for actually estimating OR as well. And this is actually the plot that you get with the same date up to the 3rd of September from that package as well. So, and we looked at all of those, and then we actually would have presented the results of the modeling would have been presented the the range of estimates you're getting from the different models would have been presented once a week to the public in a press conference, which I might talk about more in a minute. Recently, we've now been looking at, we've got some people who are interested in agent-based modeling who are involved, and they're looking at the moment, they're looking at using agent-based modeling to model various counties and towns in Ireland to look at the effect of the disease. And the group have experience of looking at other diseases basically over time. So they have some experience already in doing agent-based modeling of diseases in local areas in Ireland, and now they're extending this to COVID-19. So Elizabeth Hunter, who's the first author in these two papers, has become involved in the epidemiological modeling group. We also are looking at a lot of other data to see the impact of the various lockdown or restrictions that have happened. Apple and Google data and transport data have been very useful for looking at the impact of travel restrictions. The contact tracing data is being probed very deeply now to get a much better understanding of the contacts and how the disease has spread in the country. And there is some preliminary work being done. I'm actually involved in this directly with some people in University College Dublin, where I work, where they've been looking in the greater Dublin area at detecting COVID-19 in sewage. And it's quite interesting. We've recently had kind of a growth in the number of cases in Dublin in the last few weeks. And you can really see that the sewage data also showed that, that you could see the growth and the amount of COVID-19 being detected in the sewage, basically in the greater Dublin area with the methods that they've been using. So that's kind of an overview of the various modelling approaches we've been using in Ireland. And there's a few things, just kind of extra things I want to say at the end. So we would have, the people on the Irish Epidemiological Modelling Group, we would have met quite regularly, and the various modelling strands, I've mainly talked about the modelling, would have, interacted with each other a lot. The results that we would have found would have fed into the National Public Health Emergency Team, who would then have advised government. And the government have been listening very, very closely to the National Public Health Emergency Team and the advice that they've been given from them. Another interesting thing that I think has worked very effectively in Ireland is on most Thursdays, occasionally Wednesdays, at the government's press conference for COVID-19, Philip Nolan, who's the chair of the Irish Epidemiological Modelling Advisory Group, he gives a weekly update on what the models have been telling us about the COVID-19